All right, in this lesson we're going to take a look at what's called empirical formulas. And this word empirical, all that means is what's the formula of this compound in its simplest, most reduced format? Like what's the base unit? So what we're going to really be asking is how many copper atoms combine with how many oxygen atoms in this compound. Now sometimes it's easy to tell this based on where they're on the periodic table, but with copper, it's called a transition metal. It can have a couple of different forms, a couple of different charges, so it's hard to tell what format you may be looking at. So when you get some experimental data, which we have right here, we have a percent composition to go from. We know the percentage breakdown, but we don't really know the formula from this, so we're going to try to convert it. So we're going to take this data, and it's important to recognize that experimental data doesn't always come out perfect, so we're going to be looking for some general patterns. Might have to do a little bit of rounding. So the first step in this is to take whatever we have and turn into units that we can use. So I'm going to take this percentage and I'm just going to say, well, let's assume we had 100 grams total. If there was 100 grams total of this substance, then 88.5 of those grams would be copper. And I am going to change those into moles of copper. This is generally the first step in everything in chemistry. When you start dealing with numbers, you're going to find moles. Okay, so I need to turn grams into moles. That means grams needs to go down here. Okay. And 1 mole of copper weighs about 63.5 grams. Now where did I get that number? That's from the periodic table. That's its atomic mass. It's what the weight of 1 mole is. So when I divide those, I get somewhere around the neighborhood of 1.4 moles of copper. Okay, now I just did a little bit of rounding. It's not perfect and it doesn't have to be. We're just getting kind of close here. Okay, so that's how much copper I've got. Well, let's take a look at oxygen. I'm going to do the same thing. I'm going to take 11.5 grams of oxygen and turn it into moles of oxygen. So grams needs to go down here. Over here, the grams canceled out. And that's why we're left with moles of copper. So over here, we're going to have grams of oxygen cancel out. Now, 1 mole of oxygen weighs 16 grams. Okay, I don't have to write that again. I'll just erase that. Okay. And what I'm doing here is this little chart that I'm drawing is just a conversion. That's all it is. It's a little conversion table. It's kind of like what you do in what's called stoichiometry. And all I basically did was take 88.5 divided by 63.5. Here it's 11.5 divided by 16. And I'm going to end up with about 0.7 moles of oxygen. So in my theoretical 100 gram sample, I got 1.4 moles of copper right here and 0.7 moles of oxygen. Now sometimes you can tell the ratio just by looking at it. Sometimes you get these weird decimals you just can't quite see. So if you have a hard time looking at this and telling, here's what you do. You take these two numbers you got, these moles, and you find the smallest one. In this case, it's 0.7. I'm going to divide both values by the smallest one. So when I divide 0.7 by 0.7, I get 1. Okay, that's oxygen. Over here, I'm going to divide 1.4 by 0.7, and I'm going to get about 2. And this is where if it comes out to be 2.1 or 1.99, you just round it a little bit. It has to be close. And if it's not, we'll work on how to deal with that later if it's not anywhere close. So what that tells me is my empirical formula has 2 coppers and 1 oxygen atom. So the formula would be Cu2O. And there's my empirical formula.